Hello guys, to this third chapter in the Linear Control Systems course. In fact, in the first chapter we have presented the main mathematical tools needed for control, mainly the Laplace transform and Taylor development in order to linearize a system. Also we have presented the main parts of the control systems, the plan, the actuator, and its actuator, the sensors, and the control unit. In the second chapter, we have presented mainly the modeling of any system in time using the characteristic equation or the state space representation, or in frequency using the transfer function. Also, we have presented mainly the block reduction in order to reduce a system based on several blocks into one block, which is between the input and the output of the system. So this third chapter will be mainly considered to show the time domain analysis of the system. Thus, the outline of this presentation will be as follows. First, we will define the time domain analysis. Then we will go into the main two parts of the time domain systems, the first order systems and the second order systems. In the second order system, we will show mainly the system characteristics, the response characteristics for a step input, graphically and analytically. And then we will show analysis for any type of systems of order n. And at the end, we will show how to calculate the error for the step input. So, first of all, a very important remark to follow is that when we have to work in time domain analysis, we have always to calculate the closed loop system transfer function. So for the time domain response, it is divided mainly in two parts: the transient response and the steady state response. The transient response, in fact, it is not visualized in the frequency domain output. Thus, we use the time domain in order to study this usually fast part, and we focus mainly on the response time, on the stability time, and on the first overshoot time and value. As for the steady state, we mainly focus on the error. So back to the input types, we will focus mainly on three different input types: the step, the velocity, and the acceleration. And here we can see their time domain output and their frequency domain values. For the first order, in fact, they consist mainly on a real order. Also, they must be of a negative value in order to have a stable system. In fact, the stability will be treated in more details in the next chapter. However, so far we have only to make sure that the system is stable in order to study the response, the time domain response. And if it's not stable, it doesn't work to study this system, the response. Thus, in order to make sure that the system is stable, we have to verify that the poles, the closed loop poles, have negative real values. They can be complex, but in fact the real part must be negative. So when we have a step input, we can see that it is the charging response with tau. When t equals tau, we have 63% of the final value charged, and for t equals 5 tau, the system is almost fully charged. And we can also see the time domain response, the time domain output, which is 1 minus e minus at. If we have an impulse input, we'll consider the discharge function. So for the time domain, for the first order systems, we can calculate the rise time and the settling time as follow. We will go through these in more details in the next session, next slide. So far only we have to notice that we can calculate only these two values, the rise time and the settling time. As for the second order systems, the system in an open loop in the closed loop looks like that. The closed loop transfer function is always of the form omega n squared over s2 plus 2 zeta omega n s plus omega n squared, where omega n is the natural frequency and zeta is the damping ratio. In fact, in order to have two complex conjugate poles, zeta must be between 0 and 1. So here are the poles, and we can see that in the poles we have J, thus the poles are complex conjugate, and we can see also how to decompose the system in order to get the time domain output. So in fact, for a second order system, we can categorize it into 4 different outputs: the overdamping, the critically damping. These two cases are when the poles are real. The underdamped and the undamped. The underdamped first, it's when the poles are complex conjugate, and the undamped when the denom is equal to the value S2 plus a constant. So in this case it's always oscillating, but for the 4 cases the system is always stable. If we want to link them to the values of zeta, here we can see them in more details. In fact, for the overdamped system, we can see that the two poles are real. In this case, zeta is greater than 1. For the underdamped, the two poles are complex conjugate, thus zeta is between 0 and 1, strictly between 0 and 1. For the undamped, we have zeta equal to 0, and the system is oscillating in a constant way. And at last, for the critically damped systems, we have a real pole of order to the power 2, so of order 2, and here zeta is equal to 1. So if we continue, in fact, we can see that zeta for the case where we would focus our second order system study, we must have zeta between 0 and 1, and omega n is a natural frequency. Thus we represent once again the values of the poles, of the closed loop poles, and the time domain output. And here we can notice that theta equal 8 and zeta over 1 square root 1 minus zeta squared. So if we look deeper into the response of the system, we can define or determine several values as TR, TP, TS, and TD, and the maximum overshoot. Here we'll define these values. The TR, which is the rise time, it's the time needed to go from 10% to 90% of the system final value, and it's equal to 4 over zeta omega n. TP, which is the peak time, is the time required in order to the system to get to its maximum value, which is equal to pi over omega n square root 1 minus zeta squared. The maximum overshoot, or the overshoot percentage, it is the percentage by which the overshoot is bigger than the final value. In fact, this value is very important. Why? Because let's consider that we have a pump whose input voltage is between 0 and 6 volt as specified by the data sheet, and usually it works on 5 watts. So if the overshoot is above 20%, so at a certain time it will require more than 6 volts. We will notice that the life cycle of this pump will be smaller than the expected one, because it requires more voltage or more power than the one it's allowed to have. Thus, one way to configure this is to insert a controller who will limit, in fact, the overshoot percentage. And the overshoot percentage can be calculated by the following expression: is exponential minus zeta pi over square root 1 minus zeta squared times 100 in order to have the percentage overshoot. At the end, the settling time. The settling time, it is the time for which the system is considered to be stable. In some references, it is plus or minus 2%. In others, it's plus minus 5%.